Hello, AP Bio. Today we are starting on the largest section of this unit, which is about organic molecules. This covers chapters 2 and 3 in your book. Chapter 2 is kind of the introduction to carbon chemistry, and chapter 3 goes through all the different types of molecules. So that's kind of where we're going to be throughout the next week or week and a half or so. As we get started today, start by reviewing a little bit of vocab. If you need to, pause the video and go back and make sure you know what these words mean. When you think of electronegativity in AP Bio, the most important elements that you need to understand are carbon, hydrogen, oxygen, and nitrogen. So see if you can remember, we've talked about this before, out of those four elements, which is the most electronegative? Oh, hang on. We will come back to that in just a minute. Let's start this video over. Hello. Today we are starting on the next section of this unit, which is talking about how the nutrients we talked about last week are used to build organic molecules. This is by far the largest section of this unit, and it is mostly focused in chapters 2 and 3 of your textbook. Before we begin today, these are some of the vocab words we're going to be talking about quite a bit. If you need to, pause the video for a minute and go back and look some of these up. These are going to be really important as we try and understand the chemistry of life. So to start with today, we're going to talk about a few types of chemical bonds that we might have mentioned before, but they're really important when we start looking at the interactions between the molecules that build living things. These are all relatively weak chemical bonds, but they're really important to how life works. There are three types. The first one are called van der Waals interactions. You may have learned about these in chemistry as dispersion forces. It's a different word for the same thing. Hydrogen bonds, which we've talked about before, and ionic bonds. So we're going to talk briefly about each of those as we get started today. Van der Waals interactions happen when you have nonpolar molecules. So molecules that are made up of nonpolar covalent bonds. They still have slightly positive and negative regions because remember, electrons are constantly moving. So an analogy you could think of with this is if you told everybody, if you have a dozen people in a room and you tell everybody to get up and just randomly start running around, most of the time they'd be kind of scattered all over the room, but occasionally you would get these instances where everybody was on one side of the room, just randomly by chance. That happens with electrons too. As they move around atoms and in molecules, you randomly get these momentary areas of positive and negative charge. And so those molecules, because they have those momentary positive and negative charges, can stick to other molecules. And those are called dispersion forces or van der Waals forces. They're fairly weak, but since there are so many molecules that are constantly interacting, these can be pretty powerful because there are so many. So we're going to watch just a short, 4-minute video that will give you an example of how these dispersion forces can be really important in living things.
It's midnight, and all is still, except for the soft skittering of a gecko hunting a spider. Geckos seem to defy gravity, scaling vertical surfaces and walking upside down without claws, adhesive goos, or superpowered spiderwebs. Instead, they take advantage of a simple principle, that positive and negative charges attract. That attraction binds together compounds like table salt, which is made of positively charged sodium ions stuck to negatively charged chloride ions. But a gecko's feet aren't charged, and neither are the surfaces they're walking on. So, what makes them stick? The answer lies in a clever combination of intermolecular forces and structural engineering. All the elements in the periodic table have a different affinity for electrons. Elements like oxygen and fluorine really want electrons, while elements like hydrogen and lithium don't attract them as strongly. In atom's relative greed for electrons, it's called its electronegativity. Electrons are moving around all the time and can easily relocate to wherever they're wanted most. So when there are atoms with different electronegativities in the same molecule, the molecule's cloud of electrons gets pulled towards the more electronegative atom. That creates a thin spot in the electron cloud where positive charge from the atomic nuclei shines through, as well as a negatively charged lump of electrons somewhere else. So the molecule itself isn't charged, but it does have positively and negatively charged patches. These patchy charges can attract neighboring molecules to each other. They'll line up so that the positive spots on one are next to the negative spots on the other. There doesn't even have to be a strongly electronegative atom to create these attractive forces. Electrons are always on the move, and sometimes they pile up temporarily in one spot. That flicker of charge is enough to attract molecules to each other. Such interactions between uncharged molecules are called van der Waals forces. They're not as strong as the interactions between charged particles, but if you have enough of them, they can really add up. That's the gecko's secret. Gecko toes are padded with flexible ridges. Those ridges are covered in tiny hair-like structures, much thinner than human hair, called setae. And each of the setae is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do: stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness, but a gecko has about 2 billion of them, creating enough combined force to support its weight. In fact, the whole gecko could dangle from a single one of its toes. That super stickiness can be broken, though, by changing the angle just a little bit. So, the gecko can peel its foot back off, scurrying towards a meal or away from a predator. This strategy, using a forest of specially shaped bristles to maximize the van der Waals forces between ordinary molecules, has inspired man-made materials designed to imitate the gecko's amazing adhesive ability. Artificial versions aren't as strong as gecko toes quite yet, but they're good enough to allow a full-grown man to climb 25 feet up a glass wall. In fact, our gecko's prey is also using van der Waals forces to stick to the ceiling. So the gecko peels up its toes and the chase is back on.
All right, so that just gives you a little bit of an idea of how those forces work and how they can kind of add up to lead to some really important effects in living things. Now we're going to come back to a couple of those vocab words that you looked at. When you think about electronegativity in biology, the most important elements to remember are the relative electronegativities of carbon, hydrogen, oxygen, and nitrogen. So out of those four, do you remember which one is the most electronegative? Hopefully you remember seeing this before. If not, this is definitely something that you need to know, memorize, remember. Out of those four, oxygen is the most electronegative, followed by nitrogen. And then carbon and hydrogen are about equivalent. They're the least electronegative of those elements. These are four of the most important building blocks in living things, which is why we focus on these four. And the important thing to remember here is that when you have two elements that bond that have different electronegativities, that is when you get a polar covalent bond. So if you have a bond between nitrogen and carbon, they have different electronegativities, so that's a polar covalent bond. The same would be true of a bond between oxygen and carbon or oxygen and nitrogen. Those would both be polar covalent bonds. And the same would be true of an oxygen-hydrogen bond or a nitrogen-hydrogen bond. Anything where one element is more electronegative than the next is going to give you a polar covalent bond. an example of that can be seen in a water molecule. The covalent bond is this bond right here between the hydrogen and the oxygen. And because the oxygen is so much more electronegative, you can see it pulls more of the negative charge and has that partial negative charge, which leaves a slightly positive charge on the hydrogen. And so that combination or that polarity of those covalent bonds within a water molecule allow that water molecule to form a hydrogen bond between the positive end of one water molecule and the negative side of another. That can happen between two water molecules, like we see here, between the positively charged hydrogen and negatively charged oxygen, or between water and a different molecule. This is an ammonia molecule that has a negatively charged side by the nitrogen, which is attracted to the positive part of water. So these types of interactions are important in how certain types of molecules, like we talked about ammonia and the nitrogen cycle, how that interacts with water in the soil so that that nitrogen can be taken up by plants. Lots of other elements that living things need exist as ions. And so when the electronegativity between two elements is really different, one of them is actually strong enough to completely strip the electrons away from another, which creates two ions, which is just a charged atom or molecule. If it's positively charged, we call it a cation. And if it's negatively charged, we call it an anion. So the anions are the ones that took the electrons away from the cations. When these two attract each other, that forms an ionic bond. So that's an attraction between two particles, either atoms or molecules, that are actually charged. These bonds are really strong when they're dry. They're actually stronger than covalent bonds then. But remember, in living things, they're almost always in water, since living things are mostly made of water. And they're not nearly as strong in water, because the water molecules can actually surround those ions and separate them through hydrogen bonding. So this shows you in the middle here, you could imagine this as a clump of something like salt, sodium chloride. The sodium is positively charged ion. The chloride is the negatively charged ion. When you put salt into water, the negatively charged particles, those would be the chlorides, are attracted through hydrogen bonding to the positive sides of the water molecules, and they kind of get surrounded and pulled away. And the positive ions are also surrounded by water molecules. So ionic substances dissolve really easily in water. Many of the things that living things need, especially these trace elements that we talked about a couple days ago, exist in an ionic form. And so it's important to understand that idea of ionic bonding and how these ions can dissolve in water when we talk about how living things take in the nutrients that they need. Water can dissolve anything that has a charge, a slight charge or a complete charge like an ion. And that's why water is referred to as the universal solvent. So there are a couple of vocab words on here to review. The most important thing to remember about water is that anything that is either polar or ionic can participate in water's hydrogen bonding. If it has slight positive and negative regions, it will dissolve in water. Even if a molecule isn't completely polar, if it has partial regions of positive and negative charge, it will still mix in with water, and it's attracted to those water molecules. So we call those hydrophilic molecules. Molecules that are almost completely nonpolar are called hydrophobic. And as we start talking about the molecules that make up living things, the way that they interact with water will be really important, since living things are mostly made up of water. So here's a couple things to think about just to kind of process a little bit of this vocabulary and put it into some context. First of all, how do you know that cotton towels, like a bath towel, are hydrophilic but not polar? If you think about that, if the molecules that made up the towels themselves were completely polar, they would actually dissolve into the water. And so when they got wet, they would just totally break down and dissolve. Like if you can imagine a chunk of salt, if you pour water on it, it's going to totally come apart. Towels don't do that. They're hydrophilic, which helps them to absorb water. They're attracted to those water molecules, but they won't actually dissolve. Here's another one that gets a little more specifically at the biological importance of this. Why is it really good that our cell membranes are made of lipids? You can look at that picture and remember oil is a type of a lipid. In this picture, you can see that the oil does not mix with water, which means oil is hydrophobic. Lipids as a group are mostly hydrophobic molecules, which is really good for our cell membranes because we would not want our cell membranes to dissolve in water. The whole point of a cell membrane is to separate the inside of your cell from the outside in that aqueous environment where there's lots and lots of water. So they need to be made of substances that are not attracted to water. So now you are going to start looking at some of the actual molecules of life. If you are a House B student, you got some molecules from me on Friday that you're going to cut apart. So you're going to have 42 little cards with pictures of molecules on them. If you are a full distance learner, read the instructions in Google Classroom. You're going to be doing this activity virtually. Today, the major point of this activity today is just to start looking at the structures of these molecules. Please don't look them up. Don't use any resources. All I want you to do is make some observations of what elements make up the molecules, the shape of the molecules, patterns you see within the molecules, or common things that you see on the ends of molecules, and sort them into some groups. You get to decide exactly how many groups. There's no right or wrong answer today. The important thing is just that you have a reason for the groups that you create. We're going to be using these molecules throughout the next week and a half as we learn about the different types of organic molecules. So make sure that you keep these. If you are a House B student, maybe find a little baggie or something that you can put them in and paper clip them into their groups and bring these back with you to class. And if you're a distance learner, you're just going to return to your electronic Jamboard format for this and look at these again over the next few weeks. So go take a look at some molecules, and I will see you tomorrow.